So let's break it apart. Our perfect squares times whatever other factor is left. Well, if we square root 144, we get 12 times the square root of 30. Whenever a variable has an even exponent, we said it was a perfect square. So now we need to create our perfect square radical and whatever's left. What we're going to do is take our variable to the highest even number that is less than or equal to the current exponent. In the remaining factors radical, our variable is going to have an exponent equal to the original exponent minus the value we found here. So we're going to put the value found above. So in this example, we have x cubed. What's the highest even number that's less than or equal to 3? That's going to be our exponent here. Well, 2. I'm going to get x to, well, 3 minus 2 is 1. So I'm going to get x to the first power here. These two have to multiply to be x cubed. Now the square root of x squared, well, we take our variable and half the exponent, and we get x to the first power, and we keep our square root of x. Looking at this problem, we have the square root of a to the 15th power. What is the highest even number that is less than or equal to 15? Well, 14. We put 14 of our a's in here. How many of them are left? We had 15. We're left with just 1. What did I do really? I subtracted 14 from 15. Now we engineered this so we have all perfect squares in here. So we could take the square root and we get a to the 7th power. Perfect square factors, whatever's left. Well, x squared, the highest even number that is less than or equal to 2. Well, 2. We could put both x's here. That is a perfect square. How many of the y's can we put in our perfect square radical? Well, the highest even number that's less than or equal to 3 is also 2. How many y's are left over? Just 1. And now we've engineered this so we could take the square root. So we have x to the 2 divided by 2 power, and we get 1. We have y to the, and our exponent is divide this by 2, and we get 1. And we keep our square root of y. Okay, so we're going to set up our perfect squares and whatever's left. We'll look at the numerical part first. What perfect square from our list divides evenly into 27? And we really want the largest. Well, 9 goes into 27 3 times. How many a's can we put in our first square root? Well, the highest even number less than 3 is 2. Now we had 3 a's. We put 2 factors in here. There's only 1 factor remaining. How many b's can we put in here? Well, we can put all 6 because it's an even number. So we don't have any b's to put in here. Now, how many c's can we put in here? Well, none. The largest number, even number, less than 1, which is our current exponent, is 0. We're not going to put any factors of c in here. We're going to put all our c's there. We've engineered this so these are all perfect squares. We take the square root and we get 3. Be very careful with your number. You're looking for What number squared equals 9? But with your variables, you're taking your variable and dividing the exponent by 2. Here we have negative 2 out front. We don't want to lose it, but we want our perfect squares and whatever is left. What's the largest perfect square that divides evenly into 75? Well, 25 goes into 75 3 times. We have 2 factors of x. How many can we put in our perfect squares radical? Well, both of them. X squared is a perfect square. We have y to the 5th power. How many factors of y can we put in the first radical? Well, the highest even number less than or equal to 5 is 4. That means we have another y, and that has to go here. How many z's can we put in this first radical? Well, the highest even number that's less than or equal to 9 is 8. And we have one leftover z to put in here. Now we've engineered it, so these are all perfect squares. We could take the square root. We have negative 2 times square root of 25 is 5. Half the exponent, so we get x to the 1st power. Half the exponent, so we get y to the 2nd power. Half the exponent, so we get z to the 4th power. And of course, we keep the square root of 3yz. This problem's a little different. And what I'm going to do is, if I work on this within this fraction, I think it gets a little confusing. I'm going to take the square root of 18x squared, and I'm going to simplify that. Perfect squares, whatever's left. 9 goes into 18 2 times. X squared is a perfect square. So we get 3x times the square root of 2. So let's rewrite this. We have 9 plus, and we said this is 3x times the square root of 2 over 6. Now we have a fraction to simplify. Remember, we can only cancel common factors. And be very careful. You can never cancel a factor under a radical with a factor that is not under a radical. Okay, well, how do we simplify a fraction? We cancel common factors, which means we have to factor. The numerator has 2 terms, GCF or difference of squares. We have a common factor of 3. So we're going to factor out that 3, and we're left with 3 plus. We factored out this 3, so we just have x times the square root of 2 over 6. Factors of the numerator are 3, and 3 plus x times the square root of 2. In the denominator, 3 is also a factor. 3 goes into 6 twice. 3 goes into 3 once. And we are left with, and I'm running out of space here, but we're left with 3 plus x times the square root of 2 over 2. Now, I want to go back here a minute. And this is something we didn't talk about in the last chapter because I wanted you to get used to factoring out the GCF. However, let's take a look at it. If you have a common factor in every term of the numerator and every term of the denominator, then you can cancel. So it basically saves you this procedure we did here, and we just cancel right here. This term has a factor of 3. This term has a factor of 3. Make sure it's not under the radical. And this term has a factor of 3. So we can cancel that common factor of 3. 3 goes into 6 twice. 3 goes into 9 3 times. And 3 goes into 3 once. So we're left with 3 plus 1 times x, square root of 2, over 2. We wound up with the same answer that we had here.